Hi, my name is Jason. I am a researcher at OpenAI, and I want to talk today about a few intuitions about language models that will help you think about why they work and what's coming next. So the fundamental question that I'm going to talk about in this talk is, why do large language models work so well? And the tool that I found very helpful for trying to think about this is that if you manually inspect data, you actually learn a lot about how the model works. And one way you can think about what happens when you look at data is you're almost training your own biological neural net. And when you looked at enough data, your brain makes these observations and recognizes these patterns about the data. And I would say these intuitions that you gain from this practice are extremely valuable. As a small anecdote, when I started doing AI research in 2018, I was working on lung cancer classification. So you'd have like this biopsy slide, and you want to tell like what kind of lung cancer this patient has. And initially I said, well, if I want to train an AI to do this task, I want to be able to do the task myself. And my advisor at the time said, oh, that's totally hopeless because it takes like a pathologist years of residency to learn to do something like this. But what I did is I insisted on doing it. So I'd read like all of the journal articles related to classifying those types of lung cancer. And in the end, at that very specific pathology classification task, I was able to classify lung cancer almost at the level of a pathologist. And what I learned from doing that task of manually looking at data carried through to 3 more papers after the initial paper that I wrote. So I'll talk about 3 intuitions today. And this is the first, which is next word prediction on a large enough data set should be thought of as massively multitask learning. And for a quick review, the way you should think about how language models learn what they know is through this task called next word prediction. And it's really simple. So you have a part of a sentence. So here, the sentence is, on weekends, Dartmouth students like to. And the goal of the language model is just to predict what's the actual next word that occurred when you found that sentence on the internet. And what the language model spits out is you have this vocabulary over all the possible words in English. So you have a, aardvark, all the way to drink, study, down to zucchini. And what the language model does is it predicts what's the probability of every single word. So most words like a and aardvark, they'll be around 0, and then maybe a few words have actually a decent probability. And what we call the goodness, or like how good a language model is how close did the language model assign the probability of the actual next word, like how close is that to 1? So for example, in this sentence, if the actual next word on the internet was drink, then how good the language model is what's the probability of drink and how close is that to 1.0? And you can think about what would happen if you trained a language model on this very simple next word prediction task on a huge database, almost the entire internet. So you can imagine that in such a big database, there's going to be a lot of different tasks that will teach the language model very different things. So there'll be very easy tasks, so you can think about, there's some sentence, in my free time I like to, and the language model should learn that the probability of the word code should be higher than banana. So it'll learn some grammar. It will learn things about language. So there will be some sentence on the internet that says, I went to the store to buy papaya, dragon fruit, and then it learns to predict that the probability of durian should be higher than the probability of squirrel. So it'll know something about lexical semantics. The language model will learn world knowledge by doing this task. So there'll be some sentence on the internet that says, the capital of Azerbaijan is, and then the next word should be Baku and not London. The language model will learn traditional natural language processing tasks like sentiment analysis. So there'll be some movie review, and it says, I was engaged and on the edge of my seat the whole time. The movie was. And the language model figures out, oh, the probability of the next word should be higher for good instead of bad. It'll learn things like translation. So there might be some sentence on the internet that says the word for pretty in Spanish is, and then the language model learns to upweigh bonita compared to hola. It might even learn things like spatial reasoning. So you can imagine some sentence on the internet that says, Iro went to the kitchen to make tea. Standing next to Iro, Zuko pondered his destiny. Zuko left the. And the next word should be kitchen and not store. And it'll even learn things like math. So you can imagine on the internet there'll be an arithmetic exam, and there'll be an answer key to the exam, and it'll say, 3 plus 8 plus 4 is. And the language model will learn, oh, it should probably upweigh 15 compared to 11. And you can imagine millions more tasks like this that the language model will learn simply by trying to predict the next word in every single word in a data set. And the way to think about this is next word prediction is extreme multitask learning with millions of tasks. Now, I gave some very clean examples of tasks, but in reality, if you pick a random sentence on the internet, the tasks will be relatively arbitrary, and they'll be sort of a mix of different things. So consider this sentence from Joe Biden's Wikipedia page. So the sentence is, Biden married Nelia. And you could see when you're trying to predict Hunter, you're learning some knowledge about the world. When the language model tries to pick the word after that, it's predicting a comma. And so actually, it's getting really good at comma prediction in the process of doing this. Next word after that is a, so that's sort of a grammar task. And then, the word after that is almost impossible. It could have been student, it could have been woman, it could have been something else. And so the point that I want to make here is that even though the tasks I gave on the last slide are very clean cut, the real task that a language model will learn by doing next word prediction over a big data set is relatively arbitrary. So you have all these different types of tasks. They're a little bit weird and they're not super clean, and really doing this next word prediction task encompasses knowing a lot about the world. And here's one example of the language model will just learn what is in the data. So for example, if you look at ChatGPT in 2022, maybe at that time there wasn't a lot of information about me on the internet, and the language model would say, well, I don't know anything about Jason. And then after we update the knowledge cutoff for ChatGPT, now if you ask in this year, there is more information on the internet posted about me in 2022 and 2023. And so it'll know more information about me and be able to answer broadly about who I am. OK, so now that we know that, the second intuition I want to talk about is the fact that scaling language models in terms of compute, which is how big your model is times how much data you train it on. Scaling language models reliably improves loss, or the performance of the language model. This idea came from a paper that proposed this thing called scaling laws. And what scaling laws says is if you have a plot like this, so you have compute on the x-axis, and that's, again, data times the size of the model. The next word prediction capability of the model will continue to increase as you increase the amount of compute you use to train a model. So you can imagine a small model will have some capability. It'll improve as you train a bigger one and a bigger one and a bigger one. And my rephrase of this is basically that you should expect to get a better language model as you scale up the amount of compute that you use to train the language model. And why is this non-trivial, or why is this important? Well, I think the really important thing is the performance does not saturate like this red line here. So if the performance saturated, then you wouldn't be getting a guarantee, or you wouldn't be very confident that if you trained a larger model, you invested more money to buy more GPUs, to scrape more data, you wouldn't be guaranteed to get a better language model. But the fact that scaling laws exist makes us more confident that if you continue scaling the size of the language model, you're going to get better performance. I just wanted to show the actual plot from the scaling laws paper. So I'll walk through this. It's basically the same thing, but I just wanted to be a little bit more technical here. So on the x-axis is compute. And notice the important thing is that compute is on the log scale. So it's as you increase the amount of compute you put into the model in log scale. And the y-axis is loss. You can think of loss as sort of the inverse of capability. So the lower the loss, the better. And they train all these different models, and you can draw this sort of best fit line where if you increase the compute by a certain amount, you can predictably, you can predict how much the loss will go down. And the reason they call this scaling laws is that they found that this trend exists over 7 orders of magnitude. So it would be pretty surprising if the trend did not continue, given how long the trend has existed. I want to show an example of this from the GPT-4 paper. So what we did here is there's this OpenAI code-based next word prediction task. And again, on the x-axis is compute. The y-axis is the loss. So lower is better. And what's happening in this plot is you have on the right lower point, you have GPT-4. And then all those dots you see leading up to it are smaller size versions of GPT-4. And what this plot says is, even if you train models only up to 10,000 times less compute than GPT-4, you can predict the final performance of GPT-4. And so that's pretty powerful. So you're able to draw this law to say, hey, if I spend this much more compute trying to train this model, I can predict how good this model is going to be on a certain task. I think a question that is sort of a glaring question, but we don't have a great answer to in the AI research community is, why does scaling work? Here is sort of like a few hand-wavy explanations for this. So if you're a small language model and you don't have that many parameters, memorization is super costly. So you're training yourself, and then you come across a new task, and you have to sort of decide, is this a fact worth memorizing? I don't know. I don't have that much capacity. But if you're a large language model, you can be extremely generous in memorizing tail knowledge. So because you have so many parameters to encode the information that you're trying to learn, you can be way more generous in trying to memorize all this tail knowledge. And then the second reason why scaling helps is, say you're a small language model, you're going to be mostly focusing on first-order correlations. So you don't have that much capacity to learn all these nuances about the world. And so you're basically going to try to get the easiest things first, like grammar and maybe a little bit of basic world knowledge. But if you're a large language model, you have way more capacity to try to learn extremely complex heuristics. Like, for example, if you could try to learn math because you can do everything else so well, and you want to do this math task even better. And I want to talk a bit about how has scaling laws changed the nature of how we do AI work. So if you look at AI research 5 years ago, it would mostly be a lot of individual or small-scale projects. So you'd have teams of one or maybe a few researchers working together on something. You have this very bottom-up research culture. So as an individual researcher, you would have a lot of freedom to choose a project you work on, explore this, et cetera. And then the target 5 years ago was you would write this code only in service of having an experiment to present in a paper and submit to a conference. And with this technical paradigm shift of scaling laws, which means if you want to train the best model, you need to scale up the amount of compute and the amount of data that you have. And so look at now, you'll see that many teams have dozens of people. So you'll think about like, on one project, there'll be someone that is responsible for data collection, one person responsible for infrastructure, for evaluations, et cetera. You'll see that people work together towards one focus goal more. And often you'll see like, there'll be a research vision dictated by the company, and everyone will contribute together as a team towards that research vision. And then finally, the importance of engineering is, I would say, way more important now than 5 years ago. Because when you're working in a team, you need to run the code multiple times, and you need all this great infrastructure to scale the model. And I would say that's another change in the nature of AI research. Beyond this technical AI scaling law, I like to call this the general AI scaling law, which is, instead of next word prediction on the y-axis, you can think about the y-axis as like, this hand-wavy capability of AI. And on the x-axis isn't really compute. It's like, how much time do you give people? How much money do you invest in it? Like, how many researchers do you have working on it? And I think the point I'm trying to make here is that AI progress has been extremely steady throughout the past decades. OK, the third intuition I want to talk about is that while overall accuracy on next word prediction scales smoothly, if you separate that overall accuracy out to individual downstream tasks, you'll see that they can improve at different rates. So if you take a closer look at what overall accuracy is, you can think of it as sort of a weighted sum of all these different subtasks. So, the overall accuracy is like, some coefficient times the accuracy of grammar, times the accuracy of world knowledge, times sentiment analysis, times math ability, times spatial reasoning, et cetera. And the question to ask is, hypothetically, your accuracy goes from 70 to 80. Did the accuracy get 10% better on every single task uniformly? And I would say probably not. So you can think about, again, here's your scaling law curve. You could think about, if you have overall capability, and you decompose that trend, maybe easy tasks stopped improving at some point in the scaling law. So for example, the grammar didn't really get better from GPT 3.5 to GPT 4. They both basically had perfect grammar. And then on the other hand, you have these harder tasks, say math, where the performance improvement is sort of emergent, or you have this phase change where it suddenly starts to get a lot better. And for example, from GPT 3.5 to GPT 4, the math got a lot better. And you can look at like, OK, if you look at a sort of real-world distribution of 200 tasks from this paper called Big Bench, what do the scaling laws look like for those individual tasks? Here's what it was. So 29% of the time, you would see that the task was smoothly increasing as a function of compute. Some percent of tasks were flat, so you would see the accuracy not really improve as you scaled up compute. Some small percentage were inverse scaling, so the accuracy actually got worse as you increased the amount of compute. Some tasks were just not correlated with scale, so that was 13%. And I think the most interesting part of this pie diagram here is the emergent abilities, where you have very little improvement up to a certain threshold, and then after that, you see this big jump in performance. And here's an example of how a task might look like as an emergent ability. So the prompt here is to translate a sentence from English to Spanish. So I like to play soccer and tennis, and translate that to Spanish. And again, x-axis is model scale, y-axis is a metric of how good the translation is. And you have these three models, ADA, Babbage, and Curie ABC. And you could see, so ADA does not know how to follow the instruction of translating. So it just repeats the sentence. And then the same thing with Babbage. And the thing to note here is if you had just tried to extrapolate how Curie would do based on Ada and Babbage, you'd conclude that, oh, there's no point in training the larger model, Curie, because there's no positive trend. But in fact, Curie is able to translate the sentence perfectly, and so you see this emergent behavior where for some time, scaling doesn't help, and then after a threshold, scaling really helps. And the way that you could think about this is, let's say you have some spectrum of tasks that language models can do. So starting at the bottom, you have very basic tasks like giving facts about the very easy facts about the world, having correct grammar, translating a sentence, writing a summary. And then you have these like harder tasks like debugging code, writing a poem, doing math. And then at the very top, you have these like extremely hard tasks like writing a novel, doing scientific research, or very hard math problems. And the way that you can think about it is, as you scale on this x-axis, the spectrum of possible tasks that a language model can do, or tasks that emerge, becomes larger. So you could see with GPT-2, you could sort of only do these very basic tasks. With GPT-3 in 2020, you're able to translate a sentence or write a summary of some long piece of text. With GPT-4, you could do way more tasks. You can debug code, write a decent poem, write a coherent essay. And then you can imagine what happens when the trend continues over time. And I'll talk a little bit about how the nature of AI work has changed with these emergent abilities. So 5 years ago, it was very easy to measure how good was your AI model. So you'd have like a few benchmarks, and everyone would use the same benchmarks. And if you want to know like whether one model was better than another model, it'd be really easy to rank. So you just see like, OK, am I better on Emergent than you? And then it'd be a very simple comparison. And you train one model for every single task. So if you want to do translation, you train one model. If you want to do summarization, you train another model. And you'd have these task-specific architectures, data, and protocols that are sort of bespoke. And with this technical paradigm shift, where a single model that's trained on trained with more compute gets these emergent abilities, and now it can perform many tasks that are not explicitly specified when you train the model. And so now I would say you need to create new benchmarks to measure the capabilities of models all the time, because a new model that has a host of emergent abilities will probably saturate a lot of benchmarks. It's hard to really compare whether one model is strictly better than another. So, models can do so many tasks that one model may be better at coding, another model may be better at writing. And then companies that are working on training these models are creating an extremely general technology. So it's pretty easy to pivot between, say, a consumer product or like a coding-focused agent versus maybe enterprise product. Yeah, those are the three intuitions I want to talk about. Thanks for listening to this talk.